You know,
as I was saying, this is D-Zero. You have here a picture of the D-Zero experiment before it was hidden behind these big net concrete walls. This is where the D-Zero detector starts. It's actually all the way back behind those concrete things in there. And that's what we like. We have protons coming this way and protons coming this way. And it's about the half of the detector, the center of the detector, the collisions are just about the flags. Not above the flags, that's where the collisions are way inside. And what you see here is the very exterior wall of the D-Zero detector. The D-Zero detector is huge. It's a collaboration of about 2,000 persons. And this, what you see here, is the Muon wall that essentially is used for triggering this system, because we have so many collisions per second, and most of them we don't care about. Most of them they have nothing interesting to say. So those collisions we essentially get rid of. And we use a very sophisticated trigger system that then what collisions are worth taking into date and looking at which amount. So this is the type of things we use. And I will explain a bit here. So let me see what we start. Well, they don't have a very nice picture in here, but I guess we can do with this. So collisions coming here. At the very center of the collisions, we put a detector called the silicon detector. That detector is essentially a set of strips, wires, that allow us to tell when a charged particle passes through, it makes a hit. And so we have many layers, concentrical layers, one atop each other. And so when we look from the side, we can see that we hit this one, the other, and the other. And we can reconstruct what we call a track, the trajectory of the charged particle. And then based on that, because the whole thing is in a magnetic field, based on that we can say what the momentum of the particle is, what the momentum of the energy was of this particle that travels. This is a mock-up of the D-Zero detector. I think we can So beam comes in here, collisions are produced in the center. And right in the center here, in there is where the silicon detector is located. Outside the silicon detector, we have what's called a fiber tracker. We have some mock-up here. This is a mock-up of the fiber tracker. It's down here. So again, imagine the protons come this way and the protons come, they collide, they pass the silicon detector, and then they pass several layers of things. These are just fibers. Fibers going across from one end to the other, all around, many layers. And then these fibers are connected via subelectronics, something like this. These are all fibers coming in here, and they are feeding to this. And what that does essentially is looking at the light of the fibers. If a particle passes through, it gives some light. It's called Cherenkov light. When it passes through, it's going to leave light, we're going to catch the light. We know what position that fiber was, so we are able to say, we have one particle coming here, and then in the next layer we have another particle coming here, so we can again reconstruct the whole path of the particle. And these things are very sophisticated. They were actually designed here at D-Zero. This is the beautiful down at the bottom. And that's because in here, this is refrigerated. It's almost near zero absolute. And all the chips that we need are actually in here. And then the fibers go really all the way through. They go to the chips. And the chips are able to say how many electrons, how much light came from that particular fiber. And if the light crosses some threshold, we say, oh, that's a hit. That's gotta be a charge particle. And so we have a lot of them going to connect to each other. Then the whole thing is embedded in a big magnetic field. It can be solenoid, it's a superconducting solenoid. It provides a very high magnetic field inside. Otherwise, if we do not put a magnetic field, the collisions will happen and the particles will all go straight. But if we put the magnetic field, the charged particles will bend. So if they bend this side we know it's a positive particle. The bend the other side we know it's a negative one. And then outside all these things, calorimeters. And that's really what you see in there. What you see in there, the great thing I was showing you in the mock-up, is just big, huge calorimeters. They do nothing else than absorb energy. They don't really know exactly how this energy enters. It's just the total amount of energy that we get in the calorimeter. All around, this is an example of the calorimeter. It's of course a mock-up as well. This is much smaller, of course, but you have a lot of different things to actually measure the energy of the particles. What we do is we have one particle coming from the center, and we absorb, the particle produces a shower here, and we are able to tell based on the amount of light that we get what the energy of the particle is. So if we get the energy from here, and we get the core momentum from the flux reconstruction, we are able to tell all the parameters we need, energy, momentum of this particle. And this is a piece of what they call the shower mat system, and you see how they have fibers in there. You see all the fibers in here, and all the fibers are routed out to this. Now this is just, if you look in there, the light you see coming, it's actually the light coming from here. It's just absorbing the light so well that you can see all the things lit up. To me it's fantastic. Of course this works in a very dark environment, right? So the only time you see a spark of light is when a particle passes through one of these fibers. So this is just one part that we have the whole detector right now. The total detector has 750,000 channels, 750,000 channels. It's huge. Imagine what it is to maintain each and every channel, to make sure each channel works, to make sure the electronic works. It's a huge enterprise to actually make this work. Of course I work at CDF, which is the competing experiment, so don't say anything about it. I'm not going to say anything bad about it. So, and this is how the calorimeters look like. Big chunk pieces of gray stuff in here. When they were assembled, they were all assembled separately. Then they were squeezed in down there in what we call the assembly hall. We're going to go in there now. And they have better pictures on the wall, I believe. And then we put these big, huge muon walls. These are used to detect when a muon passes through this. And muons are very special. They do not get absorbed into the calorimeters that just pass through. But they are charged particles, so they leave a signal, a very clear signal in here. And that's what we used to say, oh, this is a very interesting event, because it has a lot of energy in the muons, so it's a muon, and muons are typically interesting. They are associated with things that are important, like the cells of the Higgs, for example. And as you know, here at D-Zero and at CDF, the top part was discovered in 1985, and that completes the idea we have of the standard model, what all the truly fundamental particles are. The top was one of them, was discovered here. Here at Fermilab we discovered about 3 particles in the last century. The last one was the neutrino tau. Right. And this is just a piece of steel, massive. And it goes outside in here, so now we can put more muon walls out in here. So this is all actually surrounded by the muon, by a wall of muon. And that's what you see here. What you see here is another layer of muon walls in here. And these walls are very simple, just a scintillator. A particle passes through, it leaves some light. We see the light, we say, oh, that's a good event. It's not the only thing we look at. Of course, we look at energy deposition in the calorimeter and things that we know are associated with the physics we want to look at. But as I was saying, we cannot possibly record so many millions of collisions per second. We need to record at most 200 collisions per second. And that's high level. That's the best we can do. So we don't have too much, elbow room to do that. So we need to trigger the system. Oh, this is part of the Run 1 forward drift chamber. You see all the wires in there? This is very similar to light. When a charged particle passes through, this is all filled with gas. So when a charged particle passes through, it will ionize the gas. So these ions will be collected by all the wires inside there, and then we're going to have some charge on the wire. So again, we keep all the channels in here, and we feed them into electronics, and we're able to tell, oh, we also know that a particle passes through here. And that's the way we reconstruct all the particles, essentially. That's by big chambers like this one, by the fiber channels that we have over there, and calorimeters, and the Muon walls. And that's what we use to do. This is an old piece of equipment. This was used in what we call round 1, finished in 1997. So it's not in use anymore, but it used to be there at some point in the past. Didn't work the last time I tried. This is a piece of the silicon. This is what we call a silicon wafer. This is the detector that's very close to the beam collision. The very first one we put next to the collision. And it's hard to see, but there are aluminum strips going on in there. Can you see them? There's an aluminum strip, a wire bond, and an aluminum strip. So this thing, we can know if a particle passes through one of the aluminum strips or the next one. So it's very precise, and it's very, very close to the collision point. So then, using this and all the other detectors outside, we are able to tell exactly what the particle passes with a very, very accurate measurement. That allows us to differentiate particles that decay immediately at the moment of the collision, particles that after the collision they travel a little bit and then decay. So this is actually one of our most useful things. We couldn't have this corner top part without this simple system. It's a huge.
Is that going to be different than the one that they look at?
Right, the one, I'm also a member of the CMS collaboration. So, and my show was to give these guys for the CMS. And the wafers, instead of being this side, are like this. You're going to see them when you go to the SIDER. SIDER stands for silicon detector. They are huge, and the size of the ones that total size is like this, then it's huge. It's going to be impossible to make that work. Being alone, of course. It's going to be fantastic. Right now we are using drift chambers in all the other experiments. We put the silicon, we're going to have a precision never achieved in the past. A lot of different particles, some amount of particles next to each other, which is like a train. Then we know the first one collides with the first one, the second with the second, and so on. Inside each band, we cannot tell which particle, we don't even know what that is. But we can tell that that particular band was the one that collided. And you know, we have a lot of particles here, a lot of here, they go through, and most of the time they don't collide. And if they collide, you know which one is which one. But they keep on going, and then they might try to collide again the next time. So this gives you a different view of the D-Zero detector. This is how it was in round 1. It's a reverse simulation done in 1990. But you can see here the different dots in there. This represents the hits, the different wires. And from the side, when things are you're going to see how a track is actually. This is how the calorimeter looks like. From the side, it's not very impressive at all. This particular calorimeter was made out of radioactive elements. It's actually a load, we're not supposed to have them. The Department of Energy gives us this, then put them in here, but when the experiment is over, we're going to have to give all the nuclear waste back to them. And because of that, it's a very nice calorimeter. It has a very high resolution, and we're able to tell things that is much harder to tell as CDS, for example. One of the best things of this video. One day, they are using a very low day. And you have to pass 7 or 8 days up and up. They have a huge error to be able to tell where the particle came from. calorimeters. And this is one of the F-discs of the silicon detector. Not only they put silicon like that, they also put discs. See, it doesn't have discs, for example. This is very nice. You're the crew chief today?
I am.
Okay. So do you mind coming up and explaining these guys?
Sure.
Something?
No, what do you want to know?
How this works?
How this works?
Everything.
Okay, everything. So basically there are 4 people on shift at D-Zero at all times. There's the DAC shifter, basically operates most of the data taking, make sure that we're continuously collecting information from the detector. And then we have 2 specialists that monitor subsystems. So there's for the tracking system, we have a shifter, and then also a shifter for the calorimeter and the Muon system. So we kind of divide up the responsibility for all of the different systems. My job as captain is to just make sure that everybody knows what's going on and that we can coordinate efforts, and that we talk with the main control room of the Tevatron, and then also with the management of the experiment, so that there's kind of a cohesive plan for what we're going to do. And then these are all the computers that you see here are just monitoring all of the different subsystems, the data acquisition system, and also what's going on in the Tevatron.
And what's that one?
So this up here is a current event display. We're not taking any data right now because there's no beam in the Tevatron. They quenched one of the superconducting magnets at about 4 o'clock this morning. They haven't recovered from that just yet. So you see nothing in our event display because, well, there's no activity going on right now. But if you were to see stuff, you would see these small little towers right here are energy deposition within the calorimeter. So that would represent a particle or a group of particles that have been created and then come into the detector.
And the cameras for that?
Oh, yeah. So we have cameras that monitor the doors in and out of the detector. We also have monitors. So up here is look at this camera right here. This is electronics inside the detector. So we can look and see the different areas of the detector, make sure that nothing's on fire, no one's in there when they shouldn't be, or make sure also that we have a lot of, all of the computers inside the detector get very hot, so we have water cooling them in radiators, just kind of the same way that you would have water cooling your engine in your car. We want to make sure that that water doesn't burst a pipe and then come flowing down through all of the computers. That has happened in the past on the system that I was working on. Well, I think actually it was 3 months after I left the last experiment, so fortunately it wasn't something that I had to deal with. Yeah. You guys have any other questions?
Questions for him?
Okay. What is a muon? So you've heard of an electron? Okay, so imagine an electron, except that it's more massive. It's 500 times 200 times heavier. I think you get that number right. So it's 200 times heavier, but in every other way, it's absolutely identical. So they decay normally, so they're not readily part of everything that we see, but at the same time they do come streaming down as part of cosmic rays. So you're not going to find them in a piece of dirt that you pick up, but at the same time, if you hold your hand out, a muon will eventually hit your hand. You won't feel it, but so if you hold out your hand, yeah, you just got hit by a muon.
You have one?
Oh yeah. Since you're like senior commander of everything, can you do all their jobs? Or?
No, I cannot. So the DAC shifter goes through, I don't know, is it a week of training? Right? A week of training to figure out all of the subsystems. I myself used to be the leader of one of the tracking subsystems, so all of the tracking stuff I can do, but the calorimeter and the Muon electronics, I ask them questions. Why isn't it working? Should I call someone to help you get it working? That kind of stuff. So the captain in general is the most useless person in the control room.
Thank you very much.
Are there any experiments running at D-Zero currently looking to detect the Higgs?
Oh yeah.
As we speak?
From the start, D-Zero, one of the objectives of D-Zero was to find the Higgs boson.
15 years ago.
15 years ago.
They started searching.
So any day now.
Here. So we're 6 months away. In perpetuity,
Right.
we are 6 months away.
For the counting room, we call it the trigger room as it is. This is the room that essentially holds all the computers that are used to do all the decisions on the experiment, to determine whether we want to keep this event or not, it does very heavy calculations on real online time to see if this event is worthy. Now, each one of these in here is a computer. It's actually two computers. It's a multi-core processor in there. We have two of them, by the way. And if you count, the total number is huge. And each one of these little guys is seen downstairs in a little square in the DAQ monitor. It's fantastic. When any one of these guys goes wrong, you see it right away. You see the color going wrong, and you can come in here and fix it right away. Again, because of the electronics it takes so much energy to make all this work, we need to cool the room to a constant temperature, and that's what the heavy air conditioners inside actually do. There was an episode in the past in which one of these air conditioners stopped working, and you can see it because the control room just light up with alarms. All this machine eventually failed, just because of the heat, and it was fantastic to see. It was very colorful. So in the past, these computers used to be big desktop computers, because there was the option at some point in the past, when the decision was made to make the experiment, the decision was, do we buy a great computer, one of these super ultra high fast computers, or do we put a lot of small computers together and make it work? And that's why we were running that, and we are still running just with a farm, what we call a farm of computers. And now we use one new, but in the past we used to have shelves with just big desktop computers, one next to each other. So you can imagine how all these look like. These are much better computers, smaller, so we can feed a lot of them, and that makes life easier for experiments.